All right, welcome everyone. Today we'll be going over a some introduction, or we'll go over some research that a lot of us officers up here have been working on recently. We'll start off with some things that Rahul's doing, and then get into the rest of us here once he has finished his delicious pizza. And this will be an open time for discussion where we'll talk about what we're doing. If you have any questions or things you think you might be able to solve or improve on what we've been working on, stuff like that. This would be a great time for more of a casual workshop that we'll be doing today.
And aside from that, this is an open time for you to ask questions generally about the process of research. If you're interested in doing that in some sort of lab, or if you're interested in doing a project yourself, feel free to ask any questions you have about the process. We're more than happy to answer them. And that's the main point of the workshop.
Perfect. Nice. Is it recording?
Hey, hey, hey. Is this on? Yeah. Let's go. Okay. We need the whiteboard for this. Can everyone see the whiteboard? All right. Well, so what I want to research over the last 6 or 7 months at this point has been in audio machine learning and how we can use audio in different to enhance healthcare in different areas in healthcare. And the the way I guess I came about this idea is comes a lot in the process. And when you guys, if you guys go into research, you guys are gonna really be facing a lot of what I went through, and these guys are gonna touch on it too, which is the actual design of the project. Getting that design is much more difficult than actually implementing, is what I've found, where you have to be unique in your idea, and your idea should not only enhance on what has come before you, it should also be something that people who come after you are going to look back on and take that forward. So it's when you come up with a project and you're in ideation phase, you're always thinking like, I have a medium. It's for me, it's audio. I have a goal that it should be something in healthcare. Now, how do I take that premise and turn it into something tangible, right? And the biggest thing in research that I have found that you have to be really good at, you become good at over time, is reading the papers and getting that literature review process might be one of the most important, if not the most important part of the whole thing, where you have to ensure not only that this idea that you have is unique to yourself, no one has done this before, and if someone has done it, I know a better way that I can do this. That's the first thing you have to ensure. The second thing that you got to make sure of is, do I have the resources to do it? Right now, once you have those two, we're all here, we're all smart, we can implement it and we get results. And then the writing, right? So for me, my initial idea was to use, and this is what you guys might face, is we were going to do a progressive supranuclear palsy classification versus Parkinson's disease. Now, do you guys know? I'm sure everyone has heard of Parkinson's, but has anyone heard of PSP? No. Okay, so PSP is very similar to Parkinson's in that the symptoms that you get when you start developing it, it becomes very hard to classify the difference between the two, where you're wondering that, okay, does this patient have PSP? Does this patient have Parkinson's? In that case, what we found is in America, it's a bit better, but if you look overseas, I can speak from experience that it's weeks, months of just observation. What is it? So we can get the right treatment for you. And by the time you figure that out, it's too late, and that's it. Right. So that was the initial idea, but I quickly found that there was one group that did it first, and they got spectacular results. Right. And you might be in that situation where I have a project idea that I've worked so hard for. I've been reading 15 papers a week. I've been getting all this knowledge. This is the one. And you end up on one that is just like, bruh, like that's the feeling of just like that heart sink feeling where I have something, but it's not going to amount to anything. But that's not the end of the road, right? You have to keep working. You have to keep finding something new. You're committed to the idea. And our next idea was, all right, what about pediatric cystic fibrosis? You talk to the people in the field that you're trying to accomplish, and whether it's you're trying to work something in systems, or in my case, healthcare, You talk to, like, I've spoken to neurologists, I've spoken to pulmonary doctors, I've spoken to medics, what in the hospitals. Like, all right, infectious disease experts, right? What are some tangible ways I can use this technology and help you guys out in a way that hasn't been done before or that can be more effective, right? And we're like, all right, we're going with cystic fibrosis because and especially with pediatric cystic fibrosis, there are ways within the speech pattern that that you can find, not only in speech, but in the cough and the sound of the lungs that you can take from the stethoscopes that, hey, that's a pattern unique to like young kids that we can actually diagnose and identify and we can classify. But what is the problem with audio machine learning? There is no audio. There's just no audio. And especially in healthcare, you have to be really unique. You have to be not unique. It's hard to get. Does anyone know why it's hard to get healthcare data? I'll open the floor. Yeah, go for it. Yeah, pretty much. Yeah, that's what it is. And so like two of us here are working in healthcare in AI applications. Like, right, like getting the data is the hardest part. You have this brilliant idea. I was talking to like the CIO of a hospital. I was like, hey, we need data. What do we need? What do I need to give you so we get this data? It's like, we have it. We need $5 million. I was like, what? I don't have that money. My school is not making this deal with you. Like, how is that going to happen? It's not going to happen, right? So you have to be more creative. And we found this data set that has a bunch of respiratory diseases, but that is recorded in a way that is not just like I coughed. It's taken directly from the lung, and there are different places in the lung and in the throat itself that signify or that can signify different diseases. So within this data set, there is one of the most common ones, which is chronic obstructive pulmonary disease, which is one of the most common diseases here in the US, asthma, URTI, LRTI, which is lower tract infection, upper tract, and throughout the chest and the throat. And we're like, okay, this might lead us to something. We have the same premise, we have the same idea, we have a data set. Now let's see what has the field done, right? We've done all this literature review. We have an idea, we have a design, we have something unique. Now, how do we move this forward, right? And so you look at what's been done, and you say, hey, we can do this better. Not only can we do this better, we can do this exponentially better than what has been done before. And we can do that in a way that no one has done it before, right? We can take advantage of the tools that we have at our disposal to augment the data set. If you guys were at the computer vision meeting, you remember me talking about data augmentation and audio machine learning. That is actually the biggest thing you have to get right. If you don't get it right, your data is screwed. Your results make no sense. Like you've augmented in the data in a way that's disproportionate that from what it's actually representing. So you have to do it right. So you look at, this is why I emphasize literature review, and I'm sure these guys will do it too. What's my time? Okay, so this is why I emphasize literature review. You see what other people have done. You take what works for them, you bring it to what you are doing, and then you make something better. So how do we make it better? So the first thing that we did is, if you guys remember me talking about it, which is why it's so big, is your design. What we're gonna do is we have all of these audio files and we have the location. So if there's any, we can actually map where that disease is based on your location and through the sound. That's the next step in our research. But what we want to do is let's just focus on this basic classification. So how do we do that? So the first thing we're going to do is we're going to augment the data. So I'm going to open up the floor to you guys. If I have like a sound, any sound, how can I make that sound like different in a way? You know, how can I change it, but it's still representative of that disease? I'll let you guys talk amongst yourselves for a few seconds. Think. There's no. No. That's a meeting. All right, what have you guys come up with? What have you guys come up with? Yeah, yeah, that's huge in the audio community is adding background noise. Well, why would that help? Kind of. Think about it like this. Let's look at it from a higher level. I'm in I'm in I'm in the doctor's office, right? There could be other sounds in the room, right? Like usually it's quiet, but you never know. If I translate this idea to like a third world country, there's so many applications for this. It should work anywhere. So if I add noise, I increase more variation into it, right? This is what it usually sounds like, but what if there's some extra noise? Can you still see what it is? That's a really good one. Anyone else? That's not a way we can augment it. That's a way we can get features out. Anyone else? All right. I'll continue for a couple more minutes because I know these guys want to go. I can keep going, but the biggest thing is we're gonna add noise. We're going to pitch shift. We're gonna time shift. We're going to um, we had like 3 or 4 more, I think, that we employed, and now all of a sudden a data set that that contains maybe like 1,000 audio files now has 10,000 audio files. Right now, there's so much more variety, and all of a sudden, that my model has more that it can train off of. Right now, how does it train off of that? Right now comes into the feature extraction. Like we're going to use a Fourier transform. And what we want to do is audio is nothing but a signal, right? And I'm not going to go into the signal processing stuff into the feature extraction into this because there's a lot of stuff behind it. But essentially, the basis for everything that we do is behind the Fourier transform. And from that, we decide how can we take this and get more out of the Fourier transform, right? And that's essentially what we do. We feed that into the model. And in my case, we use ensemble learning as our new method, our new methodology using a multi-feature CNN and an XGBoost network, which is for gradient boosting. I can go more, but I won't. And we get our output, which has been state of the art. We published the paper a few weeks ago. I need to put it on Arxiv, and I can put it in the Discord if you guys are curious into reading more about what I do and what I will continue to do. So yeah, that's what I've been doing. It's been very exciting. It's been very new, taking this from the ground, from nothing into something. If there's anything that you want to take away from this, is that if you guys have a research idea that you want to make happen, do the appropriate literature review and really get down to the nitty gritty of the stuff that, you know, that works for your idea. And if you run into a roadblock, it sounds so cliche and so like, all right, I already know this, but it's not. You don't know until you face a situation where it's like, I don't know if I can even continue this. I put in so much work, and that's the end of it. It's not the end of it. You just got to keep going and keep going and keep going. You will find something, and you will get to the finish line. So that's what I do. If you're curious about my research and if you want to help me on more, then feel free to talk to me about or DM me on the Discord. I'd be happy to talk to you guys. So that's me. Or do you guys have any questions on it? All right, cool.
Okay, cool. So my thing is also coincidentally healthcare related. We're in the same lab, but doing very different projects. So for me, trust me, I have more than one slide. Mine is on Gaussian splatting, which I'll talk about in a little bit. But has anyone heard of this? you being the exception. Gaussian splatting. Okay, maybe. What about CT scans? Okay, great. Everyone at least knows one of the two things that are important to this making sense. That's a good start. So the overview as a concept, right? We all are roughly aware of what a CT scan is. Not going into very technical details because that's not relevant or interesting. The CT scan is a way to do internal imaging. Fire a bunch of x-rays at them and be able to get a very good reconstruction of what's inside the person. This is very good for diagnosing cancer or looking for any stroke signs or anything, depending on where you do the CT scan. There's a bunch of different approaches. But there's problems associated with this. It's x-rays. X-rays are radiation, right? So as a result of doing CT scans, you often end up exposing people to 100 to 1,000 times what would often happen in terms of like pure radiation exposure compared to a single X-ray. And as a result, you can't really use CT scans as often as you would probably like. So for example, if you wanted to image children, you would not be able to use CT scans. A lot of doctors will not let you do that simply because it significantly increases lifetime cancer risk. So if, like, when I say significantly, I don't mean it suddenly becomes 8% likelihood you're going to develop cancer of some form during your life. I mean, it's fractional, but it's still like it's a significant percentage increase from the otherwise baseline. And as an example here, the average CT gives you 3 times your yearly background radiation. So just by walking around, you're exposed to radiation from the sun, from the earth, basically radioactive particles decaying, or just literally solar radiation. An average CT is going to give you 3 times as much as that. And so by and large, it's not a huge risk. I'm not going to provide scare tactics or anything here. CT scans are very useful diagnostic tools, and they've been in use for more than 50 years for good reason. But there's problems with them. So the point of the research basically is, how do we make this more usable and less problematic? And when I say problematic, I mean, of course, just general cancer risk. So that's the idea. We're trying to reduce the amount of exposure people have to radiation through imaging by integrating machine learning. You feeling good so far? This makes sense? Awesome. So the way that we do this is with a system called Gaussian splatting. Gaussian splatting basically is a way to represent a 3D scene with a bunch of points. So in this case, it's not actually points, it's 3D Gaussians. So if you guys have taken a statistics class, you guys know what the normal distribution looks like. So it's basically just that, but in 3 dimensions. And we're also going to be controlling the position, their eccentricity on the X, Y, and Z coordinates. We're going to be controlling their color. We're going to be controlling their opacity. All in all, each one of these points has 37 parameters that we can tune. And all this happens through the learning process that we've covered, through gradient descent, which we've covered extensively at this point. So whether or not you're purely familiar with it, that's the process. And the really cool thing about this is called photogrammetry, is that you're able to reconstruct this from any angle. So given some sort of video of a scene, in this case, it's a bike leaned up against a bench in a park, you're able to move the camera freely around the scene and render it live from positions that you haven't seen before, purely based off of reconstructions from images you already have. So if you guys are thinking about this a little bit, you might see how this might make sense for something like healthcare or CTs, yes? So a really cool note, you can't really see it here, but this is being rendered at 60 frames a second. So this is a scene, like the position of this camera did not occur in the original video. But the scene is being rendered at 60 frames a second and is able to represent basically any camera position that you want, looking like the original footage. And that's why it's so powerful, because we're able to represent medical images with less data. That's the really cool bit. So over on the right over here, you can see the ground truth. When I say the ground truth in this case, I mean the base data that we're training our model on. Because what we're doing basically through the learning process is we're just getting all of these points to represent the initial pieces of data that we give it and string it together in a way that is very high quality. So what you can see over here is that this is rendered based off of only 180 of those images. We got rid of half of the viewing angles. So for the original 360, you can think of it this way. We're taking an image every degree, and then we're moving the emitter, with the X-ray emitter, 1 degree. So with this, we're able to get basically identical quality. Like, you can't see it very well in the projector, but even on the crappy projector, you can see them virtually identical. There are no weird floating features or extraneous bits that don't make sense, and it would still be a very high quality diagnostic tool. And so inherently, you're able to see that we're able to reduce the total amount of images we need by more than 50%. So you're able to literally cut in half the amount of radiation you're going to be exposing someone by doing this method. And the process in the machine doesn't change. You just move you move the detector and the emitters more. Instead of doing like as many very precise shots, you just space them out more. In theory, you get the exact same thing out. And so that's the point of the research, by and large. For me, I think it's very important. It makes it so that you're able to make this type of very powerful diagnostic tool available to more people who need it. You're able to, like, this, fun fact for you, was run on a very modest PC. It was run on my PC. I have like middle of the road stuff from 5 years ago. And it ran it perfectly fine in about 15 minutes. So you're taking stuff that would be computed on the machine, run on the machine, and just offloading it to a server, which with a more powerful computer, you can reduce the amount of time this needs about 10 minutes. So you're saving time on the machine, you're saving time. I mean, not that CTs really take very long, but you're saving time on the machine, you're saving like people's exposure to radiation, you're making it more available. And really the only thing you're concerned with is time. And because you're able to live view this from any angle that you want in reasonably high fidelity, you're able to get basically the same diagnostic power without changing anything around. Does that make sense? Feeling good? Any questions about like the process of how we approached this, why we chose this, the actual thing we're basing our work off of? It wasn't clear this was already submitted for a conference. We don't have a way for you to read the paper yet. If you were interested in that, to see some more. Our paper's not on archive. It's on archive? You're sure? Since when? Wait, really? It's on archive? Oh shit. He said it would. Okay, sorry, never mind. I'm really excited about this. I thought we weren't allowed to put it up yet because it was still under review. I was petitioning from the moment we submitted to the conference to put it on archive. Okay, that's actually really good. Nice. I'm gonna post this on my LinkedIn. But yeah, no, it's really cool. You can find the paper. You just need to look up like someone go back. Oh wait. There we go. So just look up this. You'll be able to see it. There's more detailed results with a little bit of extra math. Just type this into Google. You'll be able to find the paper. Yeah, no, it's like it's very good, and I'm very, very proud of the work that we did, and I'm very happy the potential impact this is going to have, as long as people are. And yeah, I think that's the main takeaway for research is if you do end up doing this stuff, there are very tangible impacts. It's not like we're at the most prestigious university on the planet. There was around the time we submitted, actually, there was a group from, I think, Johns Hopkins who did something very similar to what we did. So directly competing, right? But you can and will have direct impact on the world around you in a very substantial way simply by doing research. If you're interested in doing this stuff, you can find applications and you can literally change lives just by being a coder. And it's more complicated than that, of course, but yeah. And that's why I really do like to encourage people to research if you're interested. It's worth trying at the very least. If you end up being dissuaded by the amount of papers you have to read, the amount of code you have to write, that makes sense. But it's a very worthwhile endeavor, and there's a lot to be gained for you and for just the world in general. Perfect. Ready. On to Kevin.
So been in this little bit less than these guys, but you know, I've still got some stuff to show for it. The stuff that I'm doing is molecular dynamics modeled with machine learning. So let's just head straight into it. The first thing that I'm going to talk about is molecular dynamics, because what is that? Essentially, it's the modeling of atoms and molecule interactions and movements. So they're moving around space, they're interacting with each other, there are different forces happening, and it's modeling these things. However, this is very computationally expensive. And a lot of the field of molecular dynamics is working on ways to speed up these processes to do more of them in less time. So our goal, the research lab that I'm part of, our goal is to simulate an entire cell, which currently takes years of simulation time. Just to motivate this problem a little bit, can someone give me a possible reason why you might want to model molecular dynamics, why someone might want to do this? Sure. Yep. Yeah. Do you have one, Dylan? Yeah. Exactly. It's to be used for further medical research. This is generally a tool, and so it can be used in further medical research for many things. Stem cells, pharmaceuticals. Yeah, it's just very useful in a lot of ways. So, let's move on to actually doing this with machine learning. The general idea of this is doing this with a graph neural network, which, if you don't know, is kind of self-explanatory. It's a neural network that functions on a graph instead of on a bunch of points, as you guys have learned that, or a bunch of data points that, as you guys have learned that neural networks do from other meetings. And so one of the things that was very important for this is a important paper on simulating complex physics with graph neural networks. If you see over here, this is physics simulations with water, slightly less viscous water, and then sand being simulated all with a neural network and therefore going a lot faster. If any of you guys have done stuff like Blender or other like 3D graphic stuff, you'll know that this kind of stuff takes a long time. Who here has done something like this with like Blender or something? Who here has worked with those kinds of softwares? Yeah, I see a couple of hands. Yeah, it takes a long time. So doing it with neural networks and speeding it up like that is a huge deal. Then the next step is to apply this to molecular dynamics. Molecular dynamics can sort of be thought of as simulating complex physics, because how they work is the atoms each have forces that they affect each other with forces and move around, and their different relationships, their different connections and stuff like that, all has different forces all applying to each other differently. And it's essentially this huge physics simulation. So when we have this, it means we can start applying it to molecular dynamics. So that's the long and short of kind of an overview of machine learning for molecular dynamics. Now, let's take a look at some of the stuff that we're specifically looking at, because this is a field that's been going on for quite a while. The main thing that's been kind of an underlying tool that we've been using through a lot of them is coarse graining. This is when you have a lot of atoms. You have a lot of atoms that are all interacting with each other, but some of them are bonded, some of them are bonded with others, some of them just move in the same direction. And oftentimes you're doing a lot of unneeded calculations, simulating the physics between things that are already bonded, things that are moving together generally, and it's quite unnecessary. So coarse graining is the idea of, let's say, think of the atoms as sand. Each one is a little grain of sand. Coarse graining, it's coarser, therefore larger grains, therefore larger kind of quote unquote atoms. I put quote unquote because they're no longer atoms, they are groups of atoms. What you're doing is you are taking the individual atoms that move together or have similar properties and taking them as one, they call it a bead. So it'll be a bead of a couple of atoms, and instead of doing calculations on the individual atoms, you'll do it on the individual beads. And this decreases the amount of things you're calculating in the simulation and speeds it up significantly, because even with neural networks, it's still pretty slow. Energy-based calculations. A lot of the kind of gradient functions, we've talked about that. We've talked about, doing the loss and stuff like that, can be done at least partially with energy, because what happens in a lot of these simulations is there will be different energy states that they're in. There'll be states of high energy, states of low energy, and you can basically tell which ones are more likely a lot of the time based on their energy state, and which one it's going to move to based on the energy state of like nearby locations. So if we take these energy calculations in, it lets us abstract a lot of the forces, force, work, energy. It's all very tightly knit, all works together very well. And we can actually do a lot of the force calculations implicitly, which again, speeds it up. Again, the name of the game here is speed, because as I mentioned earlier, currently to do what we're trying to do, it would take a year of simulation time. And that's not good. One more thing, especially this is one that specifically I've been working on a little bit, is Tika, which is time integrated component analysis. And essentially what it is you are looking at which atoms are moving in which directions together and which ones are moving in which directions apart from each other. That's very abstract, and this whole idea of Tika is very abstract, but not everyone's going to raise their hand, but who here has done calculations with eigenvectors and eigenvalues? Okay, that's a fair few people. Essentially, the idea of eigenvectors and eigenvalues is to take some kind of transformation or matrix and define it as eigenvectors or vectors. And what you can do is in higher level math, you can, like higher dimension math, you can kind of simulate some of these by representing it by representing a matrix with only the most important eigenvectors. So then we get here to Tika. Tika is a similar process where you can think of it as kind of a eigenvector deconstruction of the model of how things are moving. You know, you take the movements, you take the positions, you do essentially an eigenvalue deconstruction on it, and then you take the most important quote unquote eigenvectors, and these now represent the movements mostly. They don't really represent them all, but you can represent most of the data with a lot less stuff. And that is what is going on over here. So this is a tool for analysis. This is not actually part of the actual neural networks themselves. And that's what you guys will learn a lot if you end up doing research. A lot of the time is spent on analysis. You'll do something, you'll run your code, and you'll get some output, and you'll go, okay, what now? What does this mean? What can we do with it? And there's a lot of work to figure out, hey, what's the next step? Is this good? Is this bad? A lot of analysis that has to be done, just generally in research. And so that's a big part of what this is. Another big thing, and the final thing before I pass this on to Cohen, is one of the other techniques we used is something called WestPaw. I'm not going to go into this too much, but it is essentially a way of when you're simulating the different ways the atoms can move, you look at the most likely directions it's going to go. You look at the places that are most probable, and you simulate those more. If there's places where it's only going to every once in a while, you know those probably are not going to come up as much in simulation, so you don't need to focus on them. Otherwise, what can happen if you don't use WestPaw is you'll be, imagine, a good way to think about it is you're starting at a point. Let's use the board here. And you want to fill up the whole board, or at least that the whole board is your space. And so you start going just concentrically out as a circle, but you start getting points in the circle that like, oh, this is really unlikely. And in order to get farther out in a circle, you need to pass through that place. So instead of going concentrically, you start focusing on the parts that are more likely and expanding from those parts. That is kind of the general idea of WestPaw, which is another technique that is used in this. So again, molecular dynamics is the modeling of atoms moving and interacting. Machine learning is a huge deal that uses graph neural networks to essentially mimic the molecular dynamics. And these are some of the techniques that are used on top of that to analyze and speed up these processes. Cool. Before I pass it on to Cohen, any questions? Yes. Mm-hmm. The goal by the end of the lab is 100 times speed up ish. So a year, 100 times speed up, 3 or 4 days. 365 divided by 100. Years, it depends. But somewhere around that line, so taking it from, year-ish to under a week. Well, it's taking the atoms free floating and simulating the forces causing them to bond and then form the cell itself. So it's not just looking at a pre-made cell and having the cell just sit there. It's actually looking at a bunch of atoms sitting around and then forming the components, which will then form the cell itself, all just from the forces between them interacting. which I think is pretty cool and would be pretty exciting if we can get that stuff to happen that quickly, at least simulate. No, the closest people have gone is a, I think people have done a virus. Yeah. Yeah. What do you mean, like test how well it's working? So right now we are simulating proteins. So what we're doing is much, much smaller scale, see if it works, see if it's much faster. If the proteins are being sped up by 100 times, that doesn't necessarily mean the cell will be, but it's a pretty good indicator that we're going on the right track. So we're not going and just sitting there and being like, oh, let's see how much of the cell it makes, because not gonna make any. We haven't got that far yet. But we are testing on much smaller scale and seeing the speed ups. Does that answer your question? Awesome. Cool. In that case, I will pass it on to Colin.
All right. So I'll start off on some of the work that I've been doing most recently. This is my undergraduate thesis on maintaining explainability in model compression. Before going to the next slide, was anybody here for the responsible AI workshop that we held either earlier this quarter or sometime last quarter? Is anyone there for that meeting that remembers anything about explainable AI? All right, cool. I gotta introduce the topic all over again. So explainability is a very plays a key role in machine learning. As you guys have seen, neural networks are very complicated and you don't really understand what it's doing. They're essentially black boxes. Yes, you can look at the math that goes through them, but it doesn't really tell you how it came to a certain conclusion. It's really difficult. And in order to actually understand these, you have to use different tools. GradCam, which analyzes and SHAP perturbs the different and with these explanations. But here's a quick example for image classification. So here we have on the left a picture of someone in prison. Well, would obviously be to predict that this is a picture of a prison. And so we do so, and it comes up with the correct prediction. But now we want to ask, how was the model able to predict it? What about that image indicated that this was a prison? And so by using these different tools like GradCam and SHAP, we're able to identify what parts of the images were what caused the model to predict it. And so here, this is a heat map, also known as a saliency map, which identifies key parts of the image used in the prediction. So as you see here in the red areas is probably around here in the image where it's shows the person's head. We could kind of get an idea about the different general parts of the original image that caused this prediction. And so these explanations can be very helpful in a lot of different decisions, especially in troubleshooting. Imagine you have a self-driving car and all of a sudden it runs through a red light or causes an accident. You want to know, okay, why did it cause an accident? Well, if all we're doing is looking at model weights and biases, we're not going to be able to figure it out. However, if we're able to look at these explanations, it can tell us maybe it misclassified a human as for some reason it was looking at the wrong part of the image. It didn't even notice the person to begin with. So these explanations can play a key role in a lot of different models. And so it's really important for us to be able to maintain explainability within our methods. Another part of my project is on compressibility. So was anyone here last week for our compression workshop of networks? All right, so you'll probably recognize these slides, but there's three main ways for compressing neural networks. Essentially, neural networks can be really big. For instance, like with GPT-4 or GPT-3, there are billions of different weights. And so these just become huge models and they're really computationally expensive to run. And we can compress them to make them smaller, to be able to store them easier, run them faster, and put them on edge devices like our phones. And so there's a bunch of different methods for that. There's neural network pruning, which goes in and removes connections or neurons from the network to make it smaller by getting rid of those unused and non-important weights. Quantization, which reduces the weight. Weights are typically stored as floats, but if we can actually reduce to integers or even binary values to reduce one, how much storage these models take up, and two, how fast we can do the different matrix calculations. And finally, knowledge distillation, where we use a teacher model to train a smaller network. I'm not gonna go too into depth with all of these as we did that last week, but this is kind of the main two pieces. So model compression and explainability. And the big kind of point in this field is the concept of the compression explainability trade-off that hasn't really been studied or completely understood. And that this concept goes, when you have a full network, you typically get really good explanations to tell you why it predicted certain things. This is some examples of explanations on different images. As we see in the full network, so that second column, it predicts the explanations make a lot of sense to us. It says, hey, the top one is a bus, and that's because it's looked in that generic area, which seems like it is reasonable. And same thing with the cat and the sofa there on the bottom row as well. However, when we try to do different compression algorithms on it, so for instance, in that third column, that's knowledge distillation, the last two are pruning, accuracy stays relatively constant, meaning it did a good job compressing it. However, for some reason, when we look at the explanations, we start to see there's a large difference between the original network and these new models that are hypothetically understanding the same things, because the accuracy is about the same, but for some reason, the explanations are completely different. And so a lot of my work kind of goes around this, identifying, okay, why does this happen? Is this happening in only the old versions of compression? Because again, pruning and knowledge distillation have made huge leaps in knowledge since when they were invented, I think like 30 years ago. And so big thing is trying to actually figure out how do we compare these different explanations, identifying, okay, this method works really well for identifying, this pruning method works really well for accuracy, but it might see a change in explanations. How do we measure how good an explanation is? And the main way is to compare the original explanation to that new pruned explanation. So there's three main ways we can compare different saliency maps. The first one is mean squared error. I'm sure everyone has heard of this before. All we're doing is we're finding the difference between each pixel. Nothing too complicated here. This is just to see how different these different heat maps are from one another. Another interesting one is intersection over union, where we take a look at each of the, how many times there's a overlap. So for instance, if we took a threshold of our heat map, so any value of the heat map that's over 0.5 is considered a 1, and everything underneath it is considered 0. And we'd take the area of overlap divided by the area of union. So for instance, if there were 50 pixels where both the heat maps are 1s, that would be 50 divided by the area of union. Let's say there's 100 where the union were 1. So it'd be a 0.5 intersection over union. This helps identify, again, how different two heat maps are from one another. The final method is cosine similarity, which if you remember math back then, this is probably old pre-calculus level math, but it's been a while. This is essentially the dot product over the magnitudes of these heat maps. And so this identifies, again, how similar these maps are to one another. And we can use that to identify what type of pruning algorithms are able to, one, keep high accuracy while also maintaining the explainability of these models. Again, I've been doing a lot of coding, so it's just a quick snapshot of what this has been. It's a huge pain, especially with a lot of implementations, because I'm not trying to implement every single pruning algorithm that exists. I've been looking at their code and being able to extrapolate some of their models to test them. One of the big issues I've been that find their models in very different ways. So even though they're both, for instance, a VGG19 architecture model, they've defined them differently. So when you try to save them, you can't really compare them because they are separate models. If you want to learn more about that, you can talk to me a bit later. But here are some more examples of the different saliency maps of different prune models. So if the scrolling image on the far, that is the explanation different. So the one on the left is the pre-trained network that has our original weights, and the one on the right is our prune network that in all hypothetically should have worse explanation. So as you can see, there's not quite a great way of comparing these, because in certain places we can sort of guess that the prune network has better explanations. So it's been a big challenge to identify, okay, what can be considered better explanations than the pruned model, than the original model. So right now, I'm just testing a bunch of the different pruned models and seeing how they compare to a uncompressed model. And then from there, hopefully I can then identify a new pruning algorithm that combines everything I've learned to maintain explainability. Does anybody have any questions about that? Yeah. So the way I'm visualizing this is through saliency maps, which are generated via GradCam. And the way it does that is it looks at the gradients of the network, and that's able to tell, okay, what part of the image was important. So if we remember with back propagation, it identifies what weights are most important or how do we want to change each weight. And by doing so, we can actually identify at the different kernels what parts of the image are valued the most. Yeah. Exactly, yes. It's essentially displaying the gradients at certain levels of the network. So as you see here, these are at every single layer, we have different explanations. Typically, the final layer is supposed to have the most accurate explanations, but as we can see, if we wait for this GIF to fully complete, the final layer has a heat map of all zeros, which doesn't make any sense. Which is also why research is kind of a pain. Here, the heat maps are blank. Something happened. I don't fully understand it yet, but still working on it. This is why it's in progress. Oh, this was a quick demo I pulled up, but yeah. Does we have any other questions? I can have a couple other topics. Cool. I've done more. This is a recent piece of work I did last year, and this was on the fair augmentation of decision trees through selective node retraining. Who here has heard of decision trees before, knows the basics of them? All right, cool, everyone does. So I can quickly go through these. So essentially decision trees is a way, is a model that helps to predict a specific thing, and it goes through each node, coming up with true or false questions such as, is this person have a good SAT? Are they taller than 5'6"? All that stuff to eventually come to a leaf, which is the conclusion. And the way it's able to split these nodes or train is to do it based off of a concept called information gain, which is the difference between the entropy of the original model, original split, versus the entropy of the new split. How does everyone feel about the concept of entropy? I know I've just recognized that. All right, cool. Glad I added this slide. So entropy is essentially the measure of randomness. So imagine you were blindly picking a red or blue marble from a bag. If there are 50 red marbles and 50 blue marbles, that's quite random. There's a lot of randomness to it, and that would be a representation of high entropy. Whereas if you had a bag of 90 blue marbles and 10 red marbles, if you pick from that, you would almost always get, I think I said blue, because there's 90 blue marbles. And so that would be a case of low entropy. So essentially the goal of a decision tree is to be able to come up with a bunch of splits such that the data that falls into those different nodes have as low entropy as possible. In the perfect world, it perfectly splits the data. So at each leaf, it only contains red marbles or only contains blue marbles. So we can use the concept of information gain to measure how entropy changes. So if you look on the left, we have the original bag, which would have very high entropy because it has about 50-50 split of red and blue marbles. And as a decision tree works, we split that set of data, or all those marbles, into two smaller nodes. So if we look back at our decision tree, it splits it up. We have good GPA. If it's false, it goes left. True goes to the right. That's basically splitting our data set in half. However, our GPA is split up. And so we have our two smaller bags. And we notice the one on the left, it split it, and there's still a lot of randomness in those smaller bags. And so it didn't do a very good job at splitting. And you can measure that by taking the difference between the original entropy and the entropy of the smaller bags there. And so that would be a bad split because we didn't actually learn anything, or we didn't separate the data very well. However, if we look on the right, that's an example of a split with high information gain, because we are splitting it from a high entropy situation to two smaller bags with low entropy within them. So we're basically trying to separate our data. In the case of college admissions, we're trying to separate between good candidates and bad candidates. And so as we see here, the goal would be to find a way to split for low entropy or have maximum information gain. And that's been how the majority of decision tree models worked. However, when it comes to responsible AI, having great accuracy is not the most important thing, or it's really important, but it's not the only important thing. Another thing that's important is fairness. And fairness has to do with, is everybody treated equally? Are the people from different groups, are they treated better than others? And there's a bunch of different ways of measuring fairness, such as statistical parity. And statistical parity states that regardless of whether someone is from a minority group or a majority group, the number of times you predict them to be a positive outcome should be equal to one another. So for instance, basketball players, try and predict whether someone's going to be a good basketball players. If they have, let's say long-haired basketball players is the minority group, and basketball players with short hair is the majority. In this case, we should expect that regardless of whether or not they have short or long hair, they should be predicted to be good basketball players at the same rate. So there should be no difference. And so what this does is it essentially measures that difference. Do people with short hair get predicted to be better basketball players more often than people with long hair? I don't know, but there's a bunch of different algorithms for that. Statistical parity, equalized odds, there's a couple other ones, but there's a bunch of these concepts that need to be implemented into our models to ensure fairness and equality when we bring these models into a production scale. And so there's been a lot of research into combining these statistics with information gain when building these decision trees. And where I come in is, what if you already have a decision tree that you've made before or you like for whatever reason, and you've noticed, hey, it's not the most fair model. How can we augment it or modify the tree without completely taking it down and building from scratch? And to do so, it's kind of broken up into two pieces. We have node selection and subtree retraining. So the first part is identifying, okay, what nodes are actually causing the fairness. We have the first part. So node selection, this is where we identify nodes that are the cause of this unfairness. And we use what's called the FOT splitting criterion to identify these poor nodes. Because not only do you want to identify what nodes result in high discrimination, which is where we use the which is identical to information gain, but instead of entropy, we use statistical parity or equalized odds or some other relationship like that. We take the product of information gain and fairness gain to identify a new splitting criterion. This is how we're able to identify what nodes are both cause discrimination and aren't the most helpful for creating an accurate or separable model. So we mark those nodes and we're able to remove them or prune them from the tree. And that gets us to a point that now we have a tree that looks mostly the same, but is missing a lot of different pieces. And we can go ahead and retrain that part of the tree using a similar method as we have here. This could be interchanged, but essentially we are removing bad nodes and then retraining the parts that we removed to be both fair and accurate. And yeah, that is it. Does anyone have any questions about fair tree augmentation? Cool. Do I say? All right. Good question. Yeah, exactly. It is not the most efficient method, but you are checking through every single column at every split it. So for instance, for grad applications, it's looking, okay, can we split it by GPA? Okay, let's try to see what happens if we split at 3.5 GPA. Okay, what if we split at 3.6 GPA, 3.7 GPA? Okay, well, we got our scores for GPA. What if instead of GPA, we look at number of extracurricular activities? Split out 1 extracurricular, 2, and 3. You just do that for every single column, every single data instance. There are more efficient ways of doing so, but that's kind of the general example of the different, the best split. Yeah, so I don't know the exact term for it, but oftentimes sensitive attributes such as race or gender can be, I wouldn't say assumed, but they could be inferred based on other characteristics, such as where the person lives. So, for instance, if one area contains a lot of one racial group and they're from that area, you could predict that they're also of that race. And so there's certain things like saying, okay, if we split based off of where they live, that could be unfair to someone's race, right? Where their location, inherently location isn't seen as a sensitive attribute, it's related to a sensitive attribute like race or potentially gender. So find these secondary causes of discrimination or these sensitive attributes is often where we're finding nodes to be improved or swapped out for. Um, mhm. Yeah, so this actually is a huge field of study, and there's a bunch of different ways of training models that use discriminative data. And part of that is to, one, for instance, manually go in and say, hey, if this person is part of a minority group, I'm going to automatically boost their score by this set amount. And while that seems counterintuitive, that's shown to work really well in some cases. Other times, you can use these discriminative or measurements of fairness as part of the loss calculation. So when finding, for instance, using mean squared error cross entropy loss, you can incorporate different things like statistical parity as part of the loss function. And there's a lot of different ways to overcome that. I'm not a perfect expert on how to ensure fairness in all models, but there's a lot of different ways you can go about it. I don't know if that's what answered your question. Cool. Does anyone have any other questions? All right. All right, cool. Yeah, thank you all for coming. We'll be here for a little bit longer, so if you want to come and talk to us about more specific questions or just things in general, we're more than happy to talk about all the things that we've worked on in the past and our experiences and all that. But yeah, thank you guys all for coming, and we'll see you next week. All right, we'll come up with something we'll do next week. Hopefully it'll be fun. Yeah.
And as always, Mondays will be the Sky's No Limit workshops, the first half being a catch-up workshop. So, you know, if you are just starting, just hearing about it, it's our quarter-long competition to make an AI model or project that goes along with the theme. This quarter's theme is Rainbow Road. Plenty of opportunities to learn and make your own model and possibly win some prizes at the end. It's a really great time, and for specifically aimed at people who don't have much experience. So if you don't have much experience, we have our Monday workshops from 3 to 5 p.m. in room 506 of this building. Come stop by and join the competition. Yeah. Thank you so much.